So, in the last class, yes, yes. So, in the last class, we have seen this example. Remember? So, we have clearly seen example. Okay, for a 95% confidence interval. Fine. If for a 95% confidence, where it is, yeah. So, for a 95% confidence interval, if we take if we take sufficiently enough samples, for example, I'm taking 1,000 samples each. Like that, I'm taking 25 times. Okay, 25 times I'm experimenting. Okay, each of 1,000 samples. Agree? And if you are checking the sample means, okay, the point here is when you are taking for a confidence level of 95%, that means, what does that mean, guys? That means there is 95% probability that the confidence interval, whatever you are creating, okay, on basis of the sample mean using this formula. That means sample mean plus or minus margin of error, okay, the confidence interval which you are going to get, okay, these 25 confidence intervals, okay, 95% of the times they will be able to capture the true population, okay, and 5% of the times there is a probability that it will miss it, okay. That's the example over here, okay. So only one, you can see there is only one missing over here, but 95% of the times it is able to capture the true population. Fine. So the same thing we have studied the other day. Fine. So now if you remember when you the day when we have started learning this, okay, I have where is it? Just give me a second. Yeah. So if you see here, I mentioned to calculate this margin of error, okay, to calculate this margin of error, so there will be two scenarios. One is if you know the population standard deviation, okay, if you don't know the population standard deviation, okay. So now we are going to study the second case, okay. So now coming to the second case, earlier what was the case? That case was you have a population, okay, P. From this, you took sufficiently large samples. Okay, that means what? If the sample size is greater than 30, okay, usually they say when it is greater than 30, fine. So it's a good sample. So like that samples, if you take sufficient amount of samples and if you take the mean of all those samples, according to central limit theorem, the sampling distribution will follow a normal distribution and the mean of this sampling distribution will be more or less equal to the population mean. Okay. Do you agree for this, guys? This is a central limit theorem, right? Basically, the what we have studied. So if we take sufficiently good samples, okay, all the sampling distribution mean will be almost equal to the population mean, and the distribution follows a normal distribution. Agree? But now the point here is, in some scenarios, we may not be able to, okay, have access to this many number of samples, okay. So it might not be feasible to collect enough number of samples. In that case, we will have less number of samples. That means some 11, okay, some 15 or 8, okay. The sample size might be less than 30. Agree? I would say because it might be related to some very new area, like let's say Corona. So in the initial stages of Corona, when it was actually when it started and people did not understand like what is the root cause, so you not have much amount of population data available over there, okay. So in those scenarios it is possible that you will not get a sufficient amount of samples. Agree? In those scenarios, okay, so obviously your sample size will be less than 30. Fine. So then the problem there is, okay, the problem here is because the distribution which you get from these samples, okay, the distribution which you get from less than 30 samples, okay, will not be a perfectly normal distribution. Okay, will not be a perfect normal distribution. It will be similar to a normal distribution. Why? Because you did not have sufficient amount of samples. If at all you might have enough number of samples, then it will be a normal distribution, but you will not have here a perfectly normal distribution. Okay, and also, okay, and also the mean, whatever you are saying, the mean, okay, if that is I would like to show you the formula. Yeah, so over here, okay, so over here, if you see x bar plus or minus z alpha by 2 into rho by square root of n. Okay, so this is when you know the population standard deviation. Okay, what is this alpha? Sorry, rho. What is this rho? Population standard deviation. Okay, but in our case, we don't know the population standard deviation. Okay, so in our case, we don't know the population standard deviation. So now in that scenario, okay, in that scenario, if at all we need to go for the formula. 1 second, guys, I would like to copy paste this and explain. Yes. So now observe here. Now, when you will get what is this z alpha by 2, right? So yes, observe here carefully. We are dealing now with a case where you don't know the population standard deviation. Okay. So two scenarios. One is when you know the population standard deviation. One is you don't know the population standard deviation. So here you don't know this rho. Okay. This rho is not available. That is first point. Second point is because you don't also have the sufficiently enough number of samples. Okay, you also don't know the sufficiently enough number of samples. The distribution, whatever you are going to get, will not be a normal distribution. Okay, but it will be somewhat similar to normal distribution. Okay, it's just similar to normal distribution. Okay, so but here, if you observe this formula, what is this z coming from? If you think about it, how did we get to this z? What is z actually? Z is a critical value. Guys, are you there with me?
Yeah, Santosh.
Okay, so if you remember, z is a critical value. That means what? That means what was the concept we have used? The technique we have used earlier in earlier scenario was, because central limit theorem was saying that the sampling distribution will follow a normal distribution. Okay, so then what we did, since we already got normal distribution, we can easily convert this normal distribution into standard normal distribution. Okay, so here all x1 bar, x2 bar, all these values. Okay, so how this normal distribution is created, the sampling distribution, it's just the means, x1 bar, x2 bar, all those will be converted into corresponding z values. Correct, corresponding z values. And then we have see, if you guys forgot, let me, yeah, so here, yeah, so this diagram, so even though it's messy, but I would say the other day we have discussed from a population. Okay, so if there is a distribution which is normal distribution, we convert it into standard normal distribution. Okay, and here if we have x1 bar, x3 bar, x5 bar, that will become z values. Okay, that will become z values. And then we have for a confidence level of 95, okay, you will have confidence level is 1 minus alpha. So we have considered this shaded region. Okay, wherever you will have okay, let's say you there will be some values. Okay, so those in between it will be 1 minus alpha, because you have considered confidence level is equal to 1. Confidence level is 1 minus alpha. Okay, the remaining part will be alpha. So each side will get alpha by 2, alpha by 2. Okay. So this is possible. And then we have studied, okay, Z, we want to find out the Z, okay, which is in between minus Z by 2 and plus Z by 2, and Z is actually what? Critical value, x minus mu by rho. Okay. And because you know the population, sorry, the population standard deviation is rho, the sample standard deviation will be what? Rho by square root of n. Okay, so all these are chain reaction concepts, guys. So that's why I need to roll back. See, again, I'm showing you. Central limit theorem fundamental point is if the population mean is rho standard, sorry, what is this variance? Okay, the population variance is rho square. The sampling distribution will be rho square by n. What does that mean? If the population variance is rho square, what is population standard deviation? Rho. What is sampling standard deviation? Rho by square root of n, just square root, right? Standard deviation is just square root of variance. Okay, so this is what central limit theorem is providing us. Okay, you don't need to do anything. Okay, this is what central limit theorem is clearly saying is. Okay, because there is a possibility over here of this. Okay, we have used the same concept over here, and then we said, okay, because central limit theorem is saying the sampling distribution will follow a normal distribution. Fine. So, and in the previous class over here, we studied any normal distribution can be conveniently converted into standard normal distribution. We use that technique. Okay. So instead of finding x1 bar, x2 bar, like in which particular x bar our required mu is falling. So we have converted it into a z values. Okay. Now instead of finding x bars, we'll find some z values. Okay. And that was a scenario we studied, and we studied that this is the value you need. Okay, so mu will be falling in between x bar plus or minus z alpha by 2 rho by square root of n. Okay, so and how did you find the z values? Based upon the 95% value, so we considered 1 minus 0 0.95. All these scenarios we have done. Okay, but the main important point I would like to highlight over here is the z. How did you get this z? Z is possible. Z is present in where? It is present in standard normal distribution. It is not present in normal distribution. Z is a critical value. What is a critical value? That is it is a standard variate. That means it is the value of a particular value in the normal distribution. Okay, it's a corresponding value of a value in the normal distribution. That means if x3 bar is a normal distribution, its corresponding value will be z. That means x3 bar minus mu by rho by square root of n will be the corresponding value of x3 bar in standard normal distribution. Okay. Guys, are you there with me? Are you just following really?
Yeah, yes.
Others?
Yes, sir.
Yes, right. Okay. So the point here is all this scenario is the other day what we have studied all this that is possible, guys, only when the sampling distribution is following a normal distribution. That's my point. Okay. Only when you have the sampling distribution, that is you are taking enough number of samples from the mu. Once you have the sampling distribution is following a normal distribution, then everything is possible. From sampling you went to standard normal, from standard normal you got z values. If it is z, directly you can use the z tables. Okay, from z tables you can calculate the area and everything, and the formula, everything is done. Okay, the flow continues. But now the problem here is, now the problem we are facing over here is two things. You are not able to collect, okay? In real life, you may not be able to collect always sufficient amount of samples, okay? So what if the case, the number of samples is less than 30, okay? So in that case, what happens? In that case, obviously, you are not following the central limit theorem. Okay, central limit theorem will be applied only when you take enough number of samples. Only then the sampling distribution will follow a normal distribution. Okay, only if you get a normal distribution, you can convert it into a standard normal distribution. From there, you will get z value. But now it is not possible getting, because you don't have the enough number of samples. And also now you don't know this row. Okay, you don't know this row. And also since you don't have the normal distribution, you'll also not have this z. Okay, this is also not present because you don't have standard normal distribution. Then from where you will get this z? Fine. So there are now two issues. Getting? So now we need to convert, okay, this formula accordingly. But before that, the distribution, okay, the distribution which you are getting when the sample size is less, okay, is called t-distribution, guys. Okay, is also called t-distribution, or it's also called as students t-distribution, guys. Okay, so it's also called yeah, it's also called students t-distribution. Okay, so why it's called student distribution? It's actually the person who is studying this, right? So every time when he do some research, right? So he used to just name it as student. Okay, not sure why, because he might be teaching to his students, but not sure. He did not use his name. Normally, let's say you will have the inventor's name, right? Like Pascal, Newton, Einstein. Okay, but this guy, in all his researches, he was using the word student. Okay, so like that, his distribution slowly came into picture as student distribution itself. Okay, that's a small background. But he said that if at all you don't have enough number of samples, okay, so in that scenario, you can use a distribution which is called t-distribution, which is very similar to normal distribution. Okay, but it depends upon the number of samples you are considering. Okay, number of samples you are considering. Okay, so this is the distribution. But so it's a t-distribution. Remember that it's also called as, it's actual students t-distribution, but generally in normal sense we call it as just t-distribution. Okay, so now here the point over here is, okay, so if you see, for a t-distribution, guys, there is one more parameter that is introduced. It's called degrees of freedom. Okay, DOF, or simply DF. Okay, degrees of freedom. Now, I don't think degrees of freedom is a new word to you. Guys, do you remember somewhere in our Python class or in the initial stats class, we discussed degrees of freedom.
Yeah, Santosh.
Okay,
At the
so
time of standard deviation, like formless.
right. So just to give a recap, I told you in if x plus y use your equation like x plus 5 equal to 10, okay, it will how many variables are there? There are two variables, x and y. Okay, so variables are two, so degrees of freedom will be 2 minus 1. Why? What is freedom? Degrees of freedom means how many variables are free to take values of their own. That is a fundamental concept. That means in if x plus y equal to 10, okay, so out of these two, you have only one variable you can freely give any value you want. That means for x, if you consider x, give any value. Let's say you give 1000. The moment you give 1000, okay, now you are killing the freedom of y. Agree? Because once you fix 1000 for x, now obviously y doesn't have any option other than what? Y equal to 10 minus 1000. Getting? Minus 990. So now there is no freedom of y. Or other way. So you even if you can take any value. Okay, y, suppose if you want to give some values to y, so y has complete freedom. Give any value. Let's say you are giving 55, anything you want. Okay, but the moment you give some value, the freedom of another variable dies. Okay, it gets stopped. So that means what? Y equal to 10 minus now what? Oh, sorry, x will become what? If you give y equal to 55, okay, now x become obviously 10 minus 55 minus 45. Agree? Getting?
Yes, sir.
See, suppose x plus y plus z equal to 100. For example, you have this equation. So here, because number of variables equal to 3, the degrees of freedom will be
2.
2. That means what? Out of these three, two variables will have its freedom. That means x can take any value. Let's say some, I don't know, 90. Y can take any value, 1115, some value. Okay, these two can take, I'm just taking example of xy, you can take yz or xz, anything. Okay, so two variables will have complete choice, but the moment when you fix some values to any two variables, there is no freedom for other variable, because obviously it should confine to particular value which will satisfy this equation that will make it to 100. Okay, so this is just a background, like what the number of variables minus 1 will be the degrees of freedom. Okay, so this actually we have discussed it somewhere in the past. Okay, but I just want to give you a recap. Okay, so now in the t distribution also, Okay, in the t-distribution also, you have one more concept called as degrees of freedom. And here degrees of freedom is nothing but, okay, nothing but number of samples minus 1. Okay, here degrees of freedom is number of samples minus 1. That's it. Okay, so if the number of samples you're taking is 50, sorry, obviously it will not be 50, right? It will be less than 30. Okay, because number of if we are greater than 30, obviously it's not called a t-distribution. It is obviously, it will become a normal distribution. Okay, so if you're having 8, number of degrees of freedom equal to 7, so like that. So now here, if you see, interestingly, see what I said. I said if you have number of samples, okay, if you have enough number of samples, some let's say greater than 30, it will become a normal distribution. Okay, because your scenario is less than 30. Okay, it is similar to normal distribution, but not exactly normal distribution. Okay, so the same thing if you observe over here, see, here we will discuss in the point of view of degrees of freedom. Okay, for example, if you see degrees of freedom equal to 1, that means what? Number of samples equal to 2. Okay, see, degrees of freedom n minus 1. Okay, so number of samples equal to degrees of freedom plus 1. Okay, so if you're having df equal to 1, that means if there are 2 samples, the distribution is this one. Okay, this one. Okay, and if you're having number of samples equal to 4, so the distribution is this: 8 yellow. Okay, 20 this radium. Okay, as you keep on increasing the degrees of freedom, okay, you will reach a standard normal distribution. Okay, which is a type of normal distribution. Okay, so that's what I said. If you have enough number of samples, okay, see 1, 3, 8, 20. So that means, as you can see, the graph is moving closer. What is the last one? The topmost one is a standard normal distribution. Okay, so as you keep on increasing the number of degrees of freedom, that means what? Indirectly we are increasing the number of samples. The n is increasing. That means if you collect more and more samples, the graph will move closer and closer and closer to the normal distribution. Okay, or standard normal distribution. Getting? So if you decrease the number of samples, the graph will move away from the normal distribution. Okay, so it just depends on the number of samples you are able to collect it. Okay, so as you can see, if you increase more than 20, like after 20, like if you take 30 or 40, 50, so it follows a normal distribution. Clear, guys? Huh? Is t-distribution clear?
Yes, Santosh.
Okay, fine. So now here, considering this t-distribution, so now we need to solve 2 problems over here. Okay, one is this one. You don't have this row, and second thing is this z is not available now because it's not a perfect normal distribution. So z is not available. Okay, so this is not available. So now what happens over here is, if you don't have this row, that means population. So what is the next possible option? Sample. Okay, so instead of going for the population standard deviation, okay, we will go for the sample. Okay, this will become sample variance or standard deviation, whatever you want to take. Okay, so and instead of z over here, you will go for a new type of statistics called as t. Okay, because it is our t distribution, it's called t. Okay, and since you have for z you have z tables, for t you will have t tables. That's it. So now this formula, okay, see guys, this formula will get converted accordingly as, okay, as you might expect, x bar, okay, plus or minus, okay, in place of t, oh sorry, z, you will have t, okay, but here t, it is alpha by 2 only, okay, it is alpha by 2 only, but you have one more parameter. As I said, it is degrees of freedom. Okay, it's called degrees of freedom. What is the number of degrees of freedom, and what is the alpha by 2 value at that point? Okay, into this row will become, this row is for population. Now it will become sample standard deviation. Okay, getting? So this is a new formula you have. It is just a slight modification from the existing standard formula, the confidence interval. This is a confidence interval. Okay, so earlier Okay, so earlier you have these values. That's why it is possible. So now you don't have this row. So it will become, for the sample, it will be yes. And Z you don't have. The corresponding value will be T. But T will also have one more parameter because the number of samples will vary. Okay, sometimes you, as I said, number of samples will vary. So you can take sometimes 15, 16, 18. So the degrees of freedom will change. So that's why you also have one more uh, parameter. Okay, as the number of degrees of freedom varying, you'll also have its corresponding T value. Okay, this you will get from the T table. Okay, so is the formula clear, guys?
Yes, Santosh.
Okay, fine. So let's try quickly try to see an example. Okay, so yeah. So after this example, so we have, see, fine. So if you don't know the standard deviation of the population, you have to use the standard deviation. Okay, so let me quickly take the pen. Okay, so earlier example was when you know the population standard deviation or variance. Okay, but if you don't know the standard deviation of the population, you have to use the standard deviation of your sample as a stand-in while creating the confidence interval. Okay, so yeah, so you have to go for the sample. Okay, since the sample standard deviation may not match the population parameter, the interval will have more error when you don't know the population standard deviation. Okay, so to account for this, we use what's known as a t critical value instead of z critical value. The t critical value is drawn from what known as t distribution, a distribution that closely resembles a normal distribution, but that gets wider and wider as the sample size falls. The T distribution is available in Skype with the nickname T, so we can get the T critical value. Okay, see, that's what the important point over here is. It's also saying the same thing. Okay, so in the place of T, in the place of Z critical value, you are going to use T critical value, but the T critical value is drawn from what is known as T distribution. Okay, that closely resembles normal distribution. This point is important. Okay, let me highlight this. It is saying it gets wider and wider as the sample size falls. Okay, so see here. Same thing is happening over here. In this distribution, as a sample size is falling, observe here, guys. From 20, if you go to 1, that means when the sample size is falling, okay, 20 is what? Here, this is 20. This is 3. This is 8. This is 1. That means as a sample size is falling, the distribution is getting wider and wider. Okay, the distribution is getting wider and wider. Getting? The distribution is getting wider and wider. Okay, and if the sample size is increasing, it will become shorter and or you say thinner. Okay, and it will go to the normal distribution shape. Okay, so it's saying the same thing. It gets wider and wider. So it is available in the Skype.stats. Okay, that we are going to see. Fine. So and also you might expect the intervals will be little wider. Okay, because see what t distribution, whatever the distribution we are going to take. Okay, so whatever the distribution we are going to take, obviously it is a bit wider. Okay, so over here, if you consider this, okay, for the same distribution, okay, from because it is getting wider, okay, so the graphs will be a bit more. Okay, so the intervals of the t distribution will be a bit more when compared to the normal distribution. Why? Because in t distribution, you don't have enough number of samples. Okay, and the approximation what you are going to get from the t distribution is not that accurate as when compared to normal Z critical value. Okay, so that's why it will have a little wider confidence interval range. Okay, we'll see the same example. So I hope you remember this example, the population example. So 25 we are taking, etc., etc. But here, instead of that, what we are doing here is see np dot random dot seed 10. Okay, sample size 25 times we're taking. Okay, so and if you see, yeah, so np dot random. Okay, sample dot mean, the sample which you're taking, the sample dot mean you are collecting here. Stats.tppf. Okay, so it's where you can get the t value. Okay, t critical value. There are two things I've told you. So one is what confidence level you want to take. Okay, usually we take 95% confidence level. Okay, it will be 0.95. But apart from that, you should also tell what is the degrees of freedom. Okay, so what is degrees of freedom, guys? Degrees of freedom is nothing but number of samples minus 1. Agree? And here number of samples is 25 minus 1 is 24. Getting? So here degrees of freedom will be 24. Okay, guys, getting?
Yes.
No, right. So now, just like how you went for the Z table, so now you can go for the T tables. Okay, it's just you have T distribution table. Okay, so over here, so you'll have two things as you can clearly see. One is degrees of freedom, and remaining thing is its value, the significance value. Okay, so now over here, if you see, what is our degrees of freedom? 24. Okay, and from this degrees of freedom, okay, how you will get the alpha value, guys? Alpha value is, see, if the confidence level is 0.95, what is alpha? What is the relation between confidence level and alpha? Can anyone explain?
0.05.
Yeah, so because confidence level plus alpha equal to 1, so alpha is 1 minus confidence interval, so alpha is 0.05. And we want alpha at what? What is our formula? Alpha by 2. Agree? Because both the sides will consider. Fine. So the alpha by 2 will be 0.025.
Yes.
Okay. So now the value which we want to calculate here is from the T table, go for the degrees of freedom 24 and alpha is 0.025. Okay. So over here, if you go for the degrees of freedom 24, okay, and in this range, okay, in this row, okay, in this row, where is the alpha? Yeah, is equal to 0.025, this one. Okay, so in this row 0.025, this one. Okay, 2.064. Fine. So that will be a critical value. So over here you see, when you calculate the T critical value, so you will get the 2.063. That means 0.064. Okay. Is this clear, guys? How did we get the T critical value?
Yes,
Santosh.
sir.
Okay, cool. So the only thing, see, in Z critical value, you can directly go in what was the Z table, guys? How did the Z table look like? Okay, let me just see once. Yeah. So in Z table, what if it is like 1.5? Okay, the alpha wherever you want to calculate. So we will do 1 plus 0.05. You will divide it. Okay, you will say 1 over here 0.05. Okay, and you will say 0.05. But in Z table, sorry, in T table, as I said, it depends upon the number of samples you are going to take. That's why you will have one more parameter just called as degrees of freedom. That's it. Number of samples minus 1 will be degrees of freedom, and the corresponding alpha value. You can get its value. Okay, fine. So after that the scenario is completely same. Okay, so sample mean, what is this? What is this formula? Okay, x bar plus or minus this part. So what is this? This is a margin of error. Okay, same thing we are going to do here. Okay, sample mean plus or minus margin of error, and margin of error is what? T critical into sigma. Okay, and these are simple calculations which you can do. Okay, fine. Finally, you will get this is a confidence interval values. Okay, so these are nothing but same thing, guys. So x bar, okay, plus or minus what was the formula? T at what? Degrees of freedom, comma, alpha by 2. Okay, and here sample uh, standard deviation by square root of n. Is this a formula which we have studied? See, x plus or minus t df alpha by 2 is square root of n. Same thing. The same thing is happening over here. So if you see here, x bar is what? Sample mean. So sample mean here. See, what is this? This part is what, guys? Critical value, t critical value. T critical value. Okay. So from where you are getting T critical value? From this we are getting T critical value. Okay. So T critical value. See, but this whole thing is called margin of error, if you remember. Okay. This whole thing is called margin of error. Only this part is called T critical value. Okay. So what you are getting? see, T critical value into sigma. What is sigma? This they are calling as sigma. Okay, whatever you can call. And how you are getting S by square root of n. What is S? S is sample standard deviation. Agree? So over here, if you see sample standard deviation divided by square root of sample size, what is sample size? N. Okay, sample size n. So this particular sigma part is this. Okay, so this part is sigma they have considered. Okay, S by square root of n, sample standard deviation square root of n. Okay, you got it. After that, this they're multiplying with what? This value. This is what T critical value. From where you are getting T critical value, from here you are getting. Clear? So multiply both of these. When you multiply T critical value into sigma, you will get margin of error. The whole thing, as I said, is margin of error. Got it? So once you get the margin of error, what is left? X bar plus or minus margin of error. What is our X bar? Sample mean. Getting sample mean. From 25 samples, if you take sample mean, you will get, so sample mean plus or minus margin of error, whatever you will get, that is a confidence interval. So this is a confidence interval. Is the calculation clear, guys?
Yes, Santosh.
Okay. So now this is a confidence interval from the T critical value. So, and what is the goal over here? Our goal is to capture the mean true population. And obviously, if you remember, our true population was around 43, right? So our true population was 43.0023. Okay. So as you can see, it is able to capture clearly. But here the one more thing what we can observe is the intervals are little wider. Okay, the intervals are little wider. For example, the intervals, if you see over here, even for 25 samples, if you take, okay, this experiment, 25 samples, all the intervals are like 42, 44, 40, around 42 to 43, right? But in T distribution, okay, in T distribution, because the distribution is not normal and the sample, you don't have enough number of samples, still it will estimate based upon the T critical value, but the only thing is the intervals will be a bit wider from 47 to 48. Okay, at the same confidence level. Fine. So when using the T distribution, you have to supply the degrees of freedom. For this type of test, the degrees of freedom is equal to the number of samples. Okay, number of samples minus 1. Okay, so if you have a large sample size, the T distribution approaches the normal distribution. This is the important point, guys. Fine. So with less number of samples, you will take some samples and you will do the testing. Okay, that is called T distribution. But as the sample size increases, okay, so if you have a large sample size, so obviously this T distribution slowly becomes normal distribution. And if it is become normal distribution, okay, so the sample size is increasing, it at one particular stage it will become normal distribution. The moment it becomes normal distribution, you can use the concept of standard normal, and from there you will get the Z critical value. So once you get the Z critical value, you can directly use this formula. Directly use this formula. Agree? So, but if the sample size is decreasing, it is coming down. Okay, then obviously you lose this Z value. So obviously you should switch to this formula. Is it clear, guys? Are you understanding? So when to use Z value, when to use T value, what is T distribution?
Yes, Santosh.
Okay. So now you can see that the notice the T critical value is greater than the Z critical value. Okay. The T critical value, okay, is greater than the Z critical value. And how did you, what is the T critical value, guys? For one, yeah, the T critical, sorry, Z critical 1.95. Okay. So 1.95. For just one sample. Okay. So earlier we took only one sample. Okay. So it is 1.95. But now for the same one sample, you are having T critical value is 2.06. Why? Because if you see here, the number of sample we took here is 1000. Very sufficient amount of samples. Okay. So that's why you got the normal distribution, you will get the standard normal distribution, you will get the Z critical value, everything is happy. Okay. Directly you will get. Fine. But now, because as I said, number of samples is less than 30 usually. So here you got 25, you can see, because then it will convert it into T distribution. So that's why you'll use T values, T critical value, everything. And in this scenario, the T critical value will be a bit more. Okay. So because it is bit more, the intervals will also be wider. Okay. Why? Because if you are able to understand, see, these values, right? Alpha by 2 is what? These values, right? So if they become wider, guys, try to understand. If they become wider. Okay, if in Z value, if this is alpha by 2, but in T value, this is becoming what? 2 point something? Guys, observe here. When you take 1000 samples, when you are using Z critical value, you are having 1.95. Okay, that means what? This value, that alpha by 2, whatever you are getting, okay, that is 1.95. Fine. But here, when you're having 25 samples, okay, when you're having 25 samples, the T critical value is 2.06. That means it is increasing more. Okay, so it is increasing more. That means it is falling over here, and this minus will also fall over here. That means the width is increasing. Are you getting that?
Yes, Santosh. And also graph is also coming down.
Yes, the graph is also coming down, and this alpha by 2 values are increasing. That means if it is 1.96 over here, but if it's 2.96, so it will be this side, so it will be some 2.06. Okay, obviously this will shift here, minus 2.06. So obviously the width is increasing. If width is increasing, the confidence interval is also increasing. Okay, so you can see confidence interval is also increasing when compared to the Z value. Fine. So notice that the T critical value is larger. Okay, this allows the confidence interval to cast a larger net of lead to make up the variability caused by the sample standard deviation in place of normal distribution. Okay, same thing is saying, because you don't have the enough number of samples, so just to be on the safe side, it will give you the little wider confidence interval. Okay. Okay, so the end result is much wider confidence interval. Okay, fine. So if you have a large sample, the T distribution will approach the Z critical value. So there is little difference between using normal distribution versus T distribution. Okay, so this is here he's saying, if you have sufficiently large sample, the T distribution will always become a normal distribution where you can use Z critical. So there you not have any difference whether you use normal distribution or T distribution. Okay, because the T distribution is becoming a what? A normal distribution. So that means if you use 1000 over here, that means sample size is 1000, and if you use the same T critical values over here, this will behave like a normal distribution, because the same T critical distribution will behave like a normal distribution when the sample size is great, high. Okay, so here if you have, let's say 500, you can test this to 500, 600. So the T distribution will start behaving like a normal distribution, and the critical values will be decreasing, and this confidence will also become shorter and shorter. Okay, that's about the T critical value. And just one more technique here is, instead of doing all this, right, instead of doing all this in stats, you directly have something called as stats.t interval. Okay, so using the stats.t interval, you can just give the required values and it will give you the confidence interval. What you need to give? Our alpha 0.95 confidence level, degrees of freedom you need to give, sample mean you need to give, standard deviation estimate. That's it. Okay, so based upon these values, it will give you the 37.48. Okay, same 37.48. Okay, and yeah guys, so I would say that is a concept regarding the T distribution. Okay, I hope it's clear. Nothing new, just because scenario like where you don't have enough number of samples, we need to study few new concepts, right? So Z will become T, rho will become sample. Okay, and critical values correspondingly for the T tables. Fine. Is this clear, guys? Any doubts regarding the T distribution, T tables, anything, feel free to ask.
As of now, no, Santosh. The same like previous one. Just a sample is less.
Okay, clear it. So just, so Megan, what happens when the sample size increases for a T distribution?
It will be like normal distribution.
Okay, and what is the benefit if it becomes normal distribution?
There is no benefit, I think. The interval becomes wider.
Wider?
When
No.
we use T distribution, the interval becomes wider.
Sorry. One is normal distribution, one is T distribution. Which one will be wider according to you?
T-distribution.
T-distribution. Okay. So if the sample size is increasing more and more, this T-distribution, as you said correctly, it will become a normal distribution. So if it becomes normal distribution, what is the benefit from normal distribution? What can we get? We can get standard normal distribution, right?
Yes, sir.
From the standard normal distribution only, we will get something called as Z critical value. Because this is not possible, we are settling for T critical value. Okay, fine. You can go through the class again. Okay, so that's regarding the confidence intervals and the T distribution, Z distribution, guys. Okay, so yeah, you can go through the class and let me know if any doubts. So now we are going to start a new concept, okay, which is called hypothesis testing. Fine. So see, guys. Okay, so this is, I would say, the last module in the statistics concept. Fine, and it is, I would say, the most important concepts we are going to study over here. And you cannot expect a statistics interview without a single, at least one question from hypothesis testing. Okay, so it is very important, I would say. Okay, but it requires, it's not like a straight away concept, it's not like an equation. Fine, so but it requires some sort of intuition before you understand this. Okay, it's not directly like, it's not like a, I can't explain to you like, hey, this is probability distribution, these are its values, it's a normal distribution, or it's like these are the quantiles, these are percentiles. I cannot do this. Okay, because you need to have some background understanding on this. Okay, so fine, guys. So what all we have studied till center limit theorem, all this confidence interval. Okay, so I hope you understood that. Okay, but if there is any confusion or if you need more time, so please go through the class. Okay, and try to revise on the T distribution and just make some notes. Okay, fine. So putting that aside, now let's focus on the hypothesis testing, guys. Okay, see, now to start with hypothesis testing, see, it requires, as I said, it requires some intuition, guys. First, you need to understand what is an hypothesis testing. Fine. See, fundamentally, hypothesis testing means, see, in real life, many a times we claim many things. Okay, so let's start from the basics. Okay, so with fresh mind, try to understand these concepts so that it will be with you forever. Okay, see, in real life, okay, in real life, okay, so see, I'll just give you the intuition today. Fine, so we'll go into details tomorrow. Okay, so see, try to understand that many a times we claim many things. Okay, for example, we will say, for example, like Rohit Sharma is going to make a century in this match, as an example. Or we can say, today it's going to rain, simple example. Or this particular party is going to win. Okay, so many claims we do in our day-to-day life. So to support our claim, okay, to support our claim, there should be some evidence. Getting, to support our claim, there should be some evidence. Okay, and based upon that evidence, we can either accept our claim or reject our claim. Okay, simple words. Getting, guys? So any statement you make, okay, okay, there should be some corresponding evidence for that. Okay, so in that way, whatever statement you are making, right? Okay, so we call that as hypothesis. Okay, I'm not sure whether you have heard this word, but sometimes we say, what is your hypothesis? Okay, so it's just my idea or my guess is this. Okay, my guess is this, but that might be wrong. But we will do some test, we will try to collect some evidence, and if I'm able to collect enough evidence, I will say, hey, based upon this evidence, I am confidently saying my guess is correct. That means, for example, I will say, hey, see, in this year, Rohit Sharma played excellently. Okay, in this particular match or in last 5 matches, he is consistently making centuries. So based upon that, I am saying in this match also, he is going to make a century. Okay, so that's my hypothesis. I'm also giving you the evidence. But you can do some test. That means what? You can take from last 5 years statistics, okay, or for that particular ground in which he's playing today, okay, you can give a statistic that even though he played very well in other pitches, but in this particular pitch he failed many times. Okay, some evidence you can collect against my guess. Okay, my statement is something, but you can collect some evidence against my statement and you can try to prove I am wrong. Okay, I will try to prove I am correct. Are you getting this? Just basic intuition.
Yeah, Santosh.
Okay, so in that scenario, okay, in that scenario, we call something called as hypothesis testing, guys. That means any hypothesis you can make. Okay, any hypothesis you can make. That is any statement you can make. Okay, so and for example, see, just as an example. Okay, so I will say, no, I'm going to say from next batch. Okay, so I expect at least like 20 students in a batch. I'll say how I'll say. So like I'll say, okay, based upon this particular batch and the feedback and the reviews, okay, etc. Okay, batch one, if you're having, let's say, like 5 students, okay, I'll say batch two will be 20 at least. Okay, that's what I'm clear. This is my hypothesis. Okay, this is my hypothesis. Fine. So after that, we'll do some test. Based upon that, we will decide whether we can accept my hypothesis or reject my hypothesis. Okay, accept my hypothesis or reject my hypothesis. Okay, so this you can apply for anything, guys. Okay, see, the importance over here is, the importance of this is, for example, see, I'll tell you. If you remember, so the Coca-Cola, okay, or see, guys, I'll show you. Okay, see, this hypothesis testing, what we are studying is, right, so it is a very much used in many companies. Okay, so Coca-Cola bottle shapes. Okay, so if you see the one which you are drinking. Okay, see, this is the one. See, the one which you are drinking actually is this one. Agree? But this is a evolution of the Coca-Cola shapes. Earlier in 1899 over here, this one. Okay, then it changed to this. Okay, this. Now it is this. Okay, so I'm not sure if this is available now. Is this available, guys? Did anyone see? But few bags I used to see, they used to sell this. Can you see this now? Or are we converted to completely plastic?
It's there, sir. Now.
It's there. Okay, great. So now here the point here is see, whenever a Coca-Cola company tries to come up with a new shape of the bottle, right? So first they will understand, because the shape of the bottle is also very, very important. Okay, so we might not concern about this, but so I don't know which particular evolution, but when they changed from shape A, okay, to shape B, fine, they noticed that significantly their sales dropped. Okay, because for example, if you see, guys, I understand that taste is important, but if you see, now we are used to this particular shape. Okay, psychologically you will have a connection with this, fine. But suddenly from tomorrow, if they're serving in this shape, if they again go back to this shape, you guys tell me honestly, will you be like again willing to buy this, even though you want the taste? Okay, you are addicted to taste, but at least I'm just asking, like, will there be any effect in buying this bottle?
Yeah, Santosh, somewhat it will
Yeah,
affect.
somewhat, right? Because the way how you hold this will give you a different feeling. The way how you hold this will give you a water bottle feeling.
Yes.
Fine. So it's not always about the taste. It's also the connection with that, right? So everything, the bike. So for example, see the bike, guys. So bike is bike. What is the functionality of bike? Just to take you from point A to point B. But the shape definitely matters, right? The way how the seating is arranged, the way how the handle is arranged, everything will matter. And that will directly affect the sales and the profit. Getting? So in one particular year, when the shape of a bottle got changed, the sales got significantly dropped. So then again, Coca-Cola company has made some survey and they understood, hey, why what's happening? So they said, they understood from the review that when they hold the bottle, right? So for example, in this shape, the people were feeling a sense of connecting. I would say the sense of emotion. Okay, they had with the Coca-Cola, but when it got changed, right? So this becomes like any other bottle. Fine. So that's why they might not consciously take the decision, but somewhere, they will lose that connection. Fine. So for example, see, from tomorrow they start serving in this type of bottle. Okay, see this one. This is very different. Fine. So see this. For example, if you see the bottles shape, so this is very much different, as you can see. Fine. So today I think we are getting this one, but 1990. See, there is consistent change. Fine. So now the point I'm trying to make over here is, okay. So whenever they are shifting from over each from one shape to other. So what they will do is, see, I'm not saying exactly they will do that, okay, but there is a scenario, okay. They will say, hey, if I change my shape, the sales will increase. That is hypothesis. Anybody will make that hypothesis. The Coca-Cola will say this is hypothesis. Okay. So they will start testing. Okay. And if at all they collect sufficient evidence to prove that, okay, the statement, whatever we are making, it is true, then they will accept this statement, guys. Otherwise, they will reject this statement. Simple. Agree? Similarly, because if I will claim that, hey, in the lace packet, okay, in the lace packet, 80% of it is just air. Okay, for example, I'll just claim it. I'll do certain test, and based upon that, I will accept this or reject this. Okay, that is simple hypothesis testing. You're making a hypothesis, you're doing some test. Based upon the test, you are able to accept your hypothesis or reject your hypothesis. Is that clear?
Yes, Santosh.
Okay. So now, see, in our day-to-day life, we often hear statements like Dhoni is better than captain than his contemporaries, or motorcycle company claiming that a certain model gives an average mileage of 100 per liter, etc. A toothpaste company claiming to be the #1 brand suggested by dentist. Okay, so let's suppose. Okay, so is it like assuming and providing? Is it like assuming and providing? Yeah, you are assuming. No, it's not assuming, Sirisha. You are making a statement. See, now toothpaste company is saying, hey, my brand is the #1 brand suggested by dentist. Okay, that is not assuming. They're not assuming. They're giving you a statement clearly. And they should support this statement. If you ask, hey, how can you say that your brand is the #1? They will say, they'll show you the evidence. See, this is my success ratio. These are my recommendations. This is the number of people who are using. This is my number of doctors, or we have this many connections with the hospitals. Based upon all these scenario, we can say that we are standing in #1 place in the market. Okay, so it's based upon the evidence. Okay, so there are no assumptions over here. Okay, so this. Now let's suppose you have to purchase a motorcycle and you have heard about the above claim and made by the motorcycle company. Would you just go and buy it, or rather look for a proof? Agree? Motorcycle company is claiming this, but how would I believe that? Okay, I would go and check for the proof. There must be a parameter based upon on which one would judge the correctness of the statement. Okay, in this case, our parameter will be average mileage. And when you use to check the statement is made actually true or just a hoax. Okay, so here fundamentally hypothesis is just a statement, assumption or a claim. Okay, what about the value of the parameter. Okay, so value of the parameter. Fine. So an hypothesis is an educated guess about something in the world around you. It should be testable either by experimental or observation. Fine. So it's a statement which you're giving. Like if you see if you're thinking how it is related to our concept. So just we'll come there, but just to give an idea, I'll say, hey, the mean of this particular distribution is not greater than, should be definitely less than 50. I'll just claim. Okay, then you will do some test and you will decide whether it is less than 50 or greater than 50. Or I will say, hey, this distribution is following normal distribution. You will test and you will check that. Okay, any hypothesis statement you can just give, but you should have some evidence. If you're not providing or collecting sufficient evidence, you will fail to prove your statement. Okay, see, like if you make the statement that Dhoni is the best captain ever, this is an assumption that we are making based upon the average wins. Okay, so and loses team under his captaincy. Okay, yeah. See, we are making an educated guess, I would say, but you can also call it assumption, I would say. Yes, Sirisha, you might be right, because see, it's not a blind assumption. That's what I mean. Okay, it cannot be random assumption, but it's an educated guess. Okay, based upon the number of average wins and losses that he has made under his captaincy. We can test this statement based upon the all the match data. Okay, so just try to understand that hypothesis is just a statement which you are making. Okay, based upon the observed values. Okay, that's just a statement. Now you need to prove it or disprove it. Okay, so I would say that's the like fundamental point over there. Okay, so we'll see detail. Okay, but just before we go, right, so there are just two types of hypothesis. One is sample and composite, guys. That means, for example, see, if at all we are saying to a specific value, that means I will say, hey, I am going to score exactly 90 marks in my exam. That is one scenario. Okay, or second scenario is I am going to score greater than 90. That is another scenario. If you are saying exact, that is called simple hypothesis. Okay. If you are giving a range greater than 90 means how much? 100? Sorry, if it is 100, 90, 91, 92, how many? I don't know. That is composite. Okay. So if you observe over here, when a hypothesis specifies an exact value of the parameter, it's a simple hypothesis. And if it specifies a range, then it's composite. That means if a motorcycle is saying, hey, my model will give an average of exactly 100 kilometers. Okay, it is simple. Why? Because if you want to disprove this, okay, if you want to disprove this, you can simply disprove by saying, if you prove that it is not equal to 100, obviously it is failing. Okay, here an average student of age is in a class is greater than 20. Okay, he's just saying greater than 20. That means it could be anything greater than 20 or 22, 24, 25, anything. Okay, so in this case, it's not the simple, it's a little composite hypothesis. Okay, it's a composite hypothesis. Okay, guys. Okay, so this is just a basic idea. Okay, we'll dive deep into this and we'll understand many interesting things like null hypothesis, what is the alternate hypothesis, and how you can accept or reject and types of errors. Oh, lots of things are there. Okay, I would say. So as I said, this will be a separate altogether separate module in the statistics section. Okay, so it will need a different type of mindset for you to understand. Okay, so this is just a basics today. So fine. So I hope just once go through the class and try to revise, and tomorrow we'll go much deeper into from next two class. Okay, so I would say this will be a continuous concepts related. Okay, so don't skip the class. Fine. So I know you guys are not skipping, but next 3 to 4 classes, I would say. So we have stats for next 4 classes. In that, first 2 classes will be related to the hypothesis testing. So we'll understand in depth what is hypothesis testing, and 3 and 4 will be some type of test. Okay, so like some chi-square test, ANOVA test. Okay, those type of tests we'll study. Okay, with that we'll complete the stats. Okay, so fine, guys. So that's all from my end. Okay, so tomorrow we'll touch upon the hypothesis and again we'll try to understand what is null and what is alternate, which is the basis. Okay, so fine, guys. That's all from my end. If there are no doubts, thank you so much.